Hello everyone, in this video we will work with AC RLC circuit, and the question asks us to determine the total impedance of the following series parallel AC RLC circuit. And the question asks us to present the total impedance in polar form and in 3 significant digits. And to be consistent, we are going to keep 3 decimal places in calculations. So if you take a look at this AC RLC circuit, we have the connection of R1, R2, resistor 1, resistor 2, a capacitor 1, a capacitor 2, an inductor 1, and an inductor 2. So they connected like this, and we need to calculate the total impedance. So before we get into anything else, I would like to draw everyone's attention to this chart. Okay, so this graph is the mathematical model for the AC RLC circuit. So what you have is you have a capacitor. That means you must find the XC, and also you must find the XL. Okay, and once you have those values, you are going to put them into the impedance form in rectangular form, and you see that the XL always take the positive part of J, and the XC will take the negative part of J. So this mathematical model translate your circuit into a mathematical language, and from there you can calculate your total impedance. So before we do that, we would like to analyze this circuit. So we want to know how the circuit is supposed to work. Alright, so I'm going to redraw the circuit like this. So I'm going to combine the R1 and the C1 as my Z1. So I know that I will have an impedance calculated by these two values, and along the way I will find this one. I define this one as Z2. Okay, I base this on the R1 and R2 here, and then I will make this part of the circuit as Z3, and you see that they are connecting to another impedance. We call this Z4, and we go back to the source. So now you see that from the source you will have the current going through this, and then it's split into two. So right here, and then is reconnected and going through Z4. So in this case what we have is we are going to have Z2 parallel to Z3. Alright, so if I redraw my circuit, I redraw it like this. Z1, and here is the Z2 parallel to Z3, and then I have the Z4, and then go back to the source. So let me rewrite the Z. So now you see that this part, right, okay, will be so Z2 parallel to Z3. And how do we find Z2 parallel to Z3? We are going to use a formula called the product over sum. So the Z2 parallel to Z3 is calculated by Z2 times Z3 divided by Z2 plus Z3. Is the product over sum formulas. Now we are going to take a look at this circuit. Okay, when I redraw it like this, you will see that the current going through this, and the current doesn't split at all. Okay, going back to the source. So that means I will have Z1 in series with these two in parallel, and then series with Z4. So I can analyze my circuit like this. Okay, so Z1 is in series with Z2 parallel to Z3, and also in series with Z4. So what formula do I get from here? The formulas I get from here will be the Z total will be equal to Z1 plus Z2 parallel to Z4. I put that in the bracket, and plus the Z4. I am sorry, I should say that this is Z3. It's because my thought was going to think of the plus Z4, so I pronounce it as Z4, but I mean it as Z3. Okay, so the Z total will be equal to the value of Z1 plus the value that you are going to find in this formula plus the Z4, because these three components are connected in series. So to work with this type of circuit, we are going to analyze our circuits first before we start putting the numbers in. So the analysis is very important. Alright, so I hope I have gone over a few times the concept of parallel and series. You base that on the circuits. Okay, so if you run the circuit through, if it's split into it's split and then it combined again, then you know that Z2 is parallel to Z3. To calculate the total impedance, we are going to use the formula of the product over the sum for two impedance. Alright, so in this case we have two values for Z2, Z3, therefore we can use the product over the sum. And in this case here, when we redraw this circuit to make it a simpler circuit, you see that you are going to have these three components connected in series. So to connect in series, our formula to calculate the total impedance will be this. Alright, so that means I am going to go to my chart and I'm going to start writing the value for Z1, and I'm going to find the value for Z2, so Z1, Z2, Z3, and Z4. Okay, so this one Z1, Z2, Z3, and Z4. And I must base on this chart in order to identify the positive part of the imaginary number in rectangular form or the negative part of the imaginary number here in the rectangular form for the impedance. So this chart will provide me with the concept, the idea, so I can translate it into my math language for the circuit. And what is the purpose of this? Then I can use the concept of using 4 basic operations of complex number to calculate my total impedance. Okay, so then I will apply this rule. If I have addition and subtraction, I will use rectangular form. If I have multiplication and division, I will use polar form. Alright, okay, so then in this case, what is my Z1? Okay, so my Z1 will be equal to the R1 plus the XC1, and I already got this. Okay, so I'm going to label them with color. So R1 and the C1, and I already have this measured in ohms. Okay, so Z1 is equal to 2.50, but I have the reactance, the capacitive reactance. Okay, the XC here is called the capacitive reactance. There are formulas to calculate this the capacitive reactance, but I just give you the value in this class. Okay, so this one will take the negative part of J. Okay, so I'm going to put a minus in front of this, so I will put a minus 12.6 J. Okay, so this one is in rectangular form. Alright, so if I go to my formulas that I have from the very beginning, so I might as well rewrite the formulas here. So Z total equal to Z1 plus Z2 parallel to Z3 plus Z4. Alright, okay. So this is the formulas that I'm going to use for this particular circuit. And Z1 is in a rectangular form. And the operation for this is just adding this. So I don't need to convert Z1 to polar. So the one I need to convert to polar would be my Z2 and Z3. Because in these formulas, I have to have a product over the sum. So that means I must have the polar form for Z2 and Z3 in order to perform that operations. Okay, so Z1 times Z2 times Z3 divided by Z2 plus Z3. Okay, alright, so I just want to make sure that I have the correct formulas up here. Z2 times Z3, Z2 plus Z3. Alright, so now we are going to find our Z2. Okay, so the Z2 will be the R2, right? Okay, and the L1. And L1 is given to us as the inductive reactance, and is also in ohms. So Z2 is equal to, R1 is a real part, so it's 2.70, and then I have an inductor here, so it will take the positive part of J. So I'm going to add that with this value, which is 8.43 J. And don't forget, Z2 is involving in the multiplication, so I'm going to convert that into polar form right away. And I use my calculator to convert, and here I have this number, and I round it to 3 decimal places to be consistent. Okay, now so I will find my Z3, and I'm going to label Z3 with another color. So I just want to make sure that I have that. Okay, so Z3 is this one. So for Z3, I don't have a resistor with that. So to write a number in rectangular form, you may want to involve the real part, which is 0. Okay, and then it is a capacitor, and given as the capacitive reactance, and you take the negative part of J, so I'm going to put as a negative 5.24 J. Okay, this is very important. We need to get this correct in order to get a correct polar expression of this rectangular form. So if we make a mistake right here, we will carry that mistake in all our calculations. So I'm using my calculator, and I have this one as 5.24, and my number for argument is negative 90 degrees. Alright, so you can use calculator and put on 0 and negative 5.24. Okay, 0 as the real part, negative 5.24 as the imaginary part, and you should end up with this. Okay, now for Z4, I just have the inductor, and it's given the inductive reactance value is 10.43. So then my Z4 will be equal to, I don't have I'm sorry, excuse me, I just need a sip of water. Okay, I don't have the values for the resistor here, so I will put it as a 0 for the real, but here is the capacitive, not a capacitive, I'm sorry, it's an inductor. Therefore, it will take the positive part of J. Go back to our chart. See here, it takes the positive part of J. So I'm going to have a positive imaginary part. So I will put positive 10.43J. Okay, so I'm very careful in doing this because I want to make sure that I don't create a mistake here and then I carry that mistake throughout the entire calculation. So do I need to convert this Z4 into polar form? No, I don't have to, because the operation involving Z4 is the addition. Okay, so most of us, when we get Z1, then we immediately convert it to polar, and we get all of this impedance. We immediately convert it to polar, but we don't have to. Okay, so the analysis tells us to eliminate some unnecessary calculation with the calculator. So this is very clear. All right, so the very first thing I will do is I will calculate that product of a sum. I will calculate Z2 parallel to Z3. Okay, Z2 parallel to Z3 will be equal to Z2 times Z3, the whole thing divided by Z2 plus Z3. So let's put in the correct number to work with. So I will put in the polar form for this. Alright, so I think I will go to the next line, so I have more space. Alright, okay. So it will be equal to 9.206. The angle is 66.303 degree, and I multiplied this with 5.24. Angle is 90 degrees, and I divided by Z2 plus Z3, and this time I have to fill it in as rectangular form. So rectangular form of Z2 is 3.70. Add that with 8.43J. Let me write it to make it clear. Okay, so this is my Z1, and then I add this with, my Z2, I'm sorry, and then I added my Z3, which is 5.24, but in this case, I am going to write it in terms of rectangular, therefore, I should write it as 0 subtract 5.24J. Okay, so just to repeat, alright, so here I have, I'm going to calculate Z2 parallel to Z3, and I'm using the product of a sum formulas for two impedance. Okay, so if we have three impedances, this product of a sum doesn't work. It's only applied for the two impedances. Okay, Z2 times Z3 divided by Z2 plus Z3. So because I perform the operation of multiplication, I put it here as polar. I perform this operation as addition, so I put the values as rectangular. Okay, now my next line, I will write that I have this number multiply with this number, and I have this 2 as addition. Okay, so I add, and here I multiply. Okay, and for this I collect the like term, I collect that with that, and I collect that with that as like term, just straight algebra. So when I do that, I should have 48.239, and the angle turn into negative 23.697 degrees, and the denominator will become 3.70, and then I add that with 3.19J. Okay, so now take a look at this operation. We are having two complex numbers divide into one another. So I'm going to apply the polar method for this. So that means I am going to convert the denominator to polar form. So I convert the denominator to polar and keep as 3 decimal places. I should have this. Alright, okay, so you use your calculator, punch this into your calculator and make sure that you get this number in a polar form. So to perform this in polar form, I'm going to remind everyone that I will take the two moduli and divide it into one another. But for my angle, for my argument, what I will do is I will subtract. Okay, and be careful. I subtract a positive value, so I just subtract that. Okay, so what I have in this case is I'm having 9.875 and the angle turned into negative 64.464 degrees. Okay, so now I'm going to go back and take a look at my final one. My final formulas is this. So here's my final formulas. I need to add these three values. Therefore, at this point, you are going to convert this into rectangular form. So convert to rectangular, I should have these values. Okay, so converting from rectangular to polar form, if we keep 3 decimal places in our calculation and we are consistent, then we will always end up with the same values. Okay, so therefore I ask everyone to work with the 3 decimal places and then round the final answer to 3 significant digits. So what is our final impedance? Z1 plus Z2 parallel to Z3, right? Okay, and we add this with Z4. So what I'm going to do is I'm going to put in the value that I have earlier. Z1 is 2.50 subtract 12.6J, and this value here is what I just found, which is 4.257 subtract 8.910J, and this value is 0 plus 10.43J. So I just put 10.43J. Alright, so now we are going to see if we can collect like term. So these are the like term. And what we do is we are going to add this 2. And my final answer should be Z total is equal to 6.757, and then I subtract that with 11.08J. Okay, so here it should be the 0. So for me to give the final answer in polar form, so this one is in rectangular, and in polar form I should have it as 13.0 minus 58.6 degree as polar. Okay, and also as 3 significant digit. Alright, so basically for this particular lesson, I ask everyone to find total impedance of this particular circuit. Okay, so it combines everything that we have learned in complex number. So we need to understand complex number in rectangular form, complex number in polar form, and we use our calculator to help us to convert between rectangular and polar form. We also learn the mathematical models of a AC RLC circuit, and this mathematical model presented to you in terms of rectangular because it's easier for you to visualize. And then from the rectangular form, you can convert that into your polar form. Okay, so according to what calculation that you have to perform using these complex number. So then you analyze your circuit. You see that you have two impedances that actually parallel to each other. So calculate that first, and then the final stage is to put this into this even simpler uh, uh, um, circuit. I'm sorry, I better drink some water. Okay, so then at this on the circuit here, you will see that Z1 connected with Z2 parallel to Z3, and they are in series, so therefore you can pull out the final formulas for this one. And the final formula for this one will allow you to know what form you are working with. So rectangular, rectangular, and after you perform this, get your number in polar form, you convert to rectangular. Okay, so this particular formula will need you to get some polar form to work with. Alright, okay, so to make things quite simple, alright, so I think I have covered everything, and I cover everything I need to say. And I apologize if I make some pause and some errors. So I just want to let everyone know that when I'm getting older, I think the numbers started to leave me and replaced with words now. So thank you everyone for your attention, and I hope you enjoyed this video, and I hope that you understand the lesson. Thank you. I appreciate it.